What up, nerds? I'm Bammed, and this is BAM CTF. Today I'm doing a special episode outside of my normal schedule. Normally I do a show called CTF and Cigars on Twitch every other Saturday at 10 a.m. Central, where I talk about CTF-related items and smoke a cigar. But today I want to specifically talk about a recent vulnerability that was released about a week and a half ago, CVE-2020-1472. Also commonly known as Zerologin. So the reason why I wanted to do an episode about this specific vulnerability is that it's kind of a big deal in that if you have a Windows domain and someone has physical access to your network and you have not patched for this yet, then they can become a domain admin just by running a Python script, which you can find on the internet right now. Now, there are a number of videos and walkthroughs and white papers and whatnot out there already that go over what the vulnerability is and how it works. But I specifically wanted to approach it from the viewpoint of a security analyst. So I know a lot of the people who have watched my videos or followed me so far are people I've worked with in the past in the security analyst field. Some of you I may have even trained because I used to do that security analyst training thing in the past, and I still do some of that. So yeah, I wanted to specifically approach this from the viewpoint of a security analyst. We're going to look at the emerging threat signature that has been released for this vulnerability, and then look at the network traffic that is captured and what it all means and what that means for security analysts, what you want to look for while you're analyzing this traffic to see if it's a true positive, false positive, success or failure, and all of that. So just to start with, I'm not going to go into a lot of detail about the vulnerability, but just a quick overview. All right, so this vulnerability was released by Secura. They made a blog post back on September the 11th. And if you scroll down to the bottom, they've got a link to a white paper where it kind of breaks down in quite a bit of detail. So it's a pretty good write-up. Explains everything related around this vulnerability and what the issue is. This is just a quick summary. So the main problem has to do with the NetLogon RPC. So there's a specific RPC function, netar server authenticate 3, where there's a client credential that is passed. Now this client credential is computed earlier in the connection when this net server request challenge and server challenge are passed back and forth. So there's a cryptographic algorithm that's used to calculate the credential, and it's based on a shared secret, which is the computer account password. So in Active Directory, every user has an account, but every computer also has an account, and there's a password associated with that. Now, all that handling of account passwords is done behind the scenes. You never really have to worry about it. You add a computer to a domain. Once it's added to that domain, the Active Directory itself kind of manages that computer account and account password. But it's in the RPC calls that are used to manage that where this vulnerability lies. So when a client computer is connecting to a domain controller via RPC, there's a handshake that takes place where a lot of the cryptographic functions are established. And part of that involves sending a 8-byte nonce from the client to the server and an 8-byte nonce from the server to the client. So that's a one-time use, randomly generated 8 bytes of data. And then the cryptographic algorithm that's used, which again, read the white paper for the details, but it takes the client challenge and the server challenge and then the computer password hash and comes up with a credential, which is also 8 bytes, and then that gets passed during the server authentication. So the vulnerability lies in that cryptographic function. Since the client, if you're a malicious client connecting to this domain controller, you have control over what you pass as the challenge. And if you pass 80 bytes, so that's 8 bytes with the data just being 00, then 1 out of 256 attempts, the credential ends up becoming zeros again. So 8 bytes of zeros as the challenge, you get 8 bytes of zeros as a credential. Not every time, but 1 out of 256 times. So even though you don't have the computer password, you can convince the server that you do, because the algorithm is based on the client challenge, server challenge, and the shared secret being the password. So hopefully that makes sense. Again, read the white paper for more details. So that's the first part of this vulnerability. So the next part of this vulnerability involves the net server password set to function, which lets you use an RPC to change that computer level password. And essentially, the vulnerability is just setting that to all zeros. So we're clearing out that computer password. So if you do this as a domain controller, you can actually connect to the domain controller and convince it that the computer you're connecting to is also the domain controller. Reset the domain controller computer level password, and then you can log in over the network as that computer account, actually knowing the password this time. So you log in normally, and then you can do additional things like you can start a replication of account passwords, because that's one of the things that domain controllers handle between themselves, is replicating all that authentication information. So you can get a dump of password hashes. Again, since you're running at the domain controller level, you can extract that golden ticket, and with the golden ticket and the password hashes, you can use a pass the hash type attack to then log in as one of the domain admins, and from there you have complete control over the network. So that's just a brief overview of what this vulnerability is. Again, there's more details in the white paper, but let's look at some. Let's look at how this is exploited. This is a script that was released by Secura. There's a link to it in the white paper. It's just a Python script that tests for the vulnerability. Now, this is only doing the first part of that, which is the authentication. It's not actually resetting any passwords. This is just a script to test to see if you're vulnerable. So we can see here the plain text. We've got 8 bytes of 0, so this is equal to exactly the hex value 00. We're doing 8 of those. That's our plain text, so that's going to be the client challenge that's passed. And then the ciphertext is also going to be 8 bytes of 0. So the idea, again, is we control one side of it, and if we control one side, we can predict that 1 out of 256 attempts, we can figure out what the ciphertext is going to be, even though we don't know the shared key being the password. Now, what does that look like in a packet capture? Okay, so here's the packet capture that we captured using a lab environment. So there's no real data being released here. So using the lab environment and using that Secura test script. So there's a connection made over port 135, so that's RPC. That's where the connection is established. When the RPC connection is established, the server then assigns a higher port, and then all the rest of the traffic occurs at a higher port. So one of the things to look for is what port number are you looking at. That is something that can be configured, so depending on the environment you're looking at, may not always be the same. But all the traffic that I've seen so far, we were looking at a source and destination port that's a high port, so that's a high ephemeral port on both sides of the network, so it's not a specific port number. So in this case, we can see we've got port 54164 and port 49670. So this 192.168.1.13, this is the attacker, and then the 192.168.0.170 is the server we're connecting to. So after connecting to port 135, we're then told by the server to connect to port 49670, and that's where all the rest of the traffic for this particular connection occurs. Then we see, thanks to Wireshark for actually decoding all this for us, but I'll break it out a little bit more in a minute so you can see what what's actually going on here when you're looking at the packets at the byte level. But we've got the net server request challenge, so this is where the client is passing its challenge to the server, and the server passes a challenge back. And if we look at the data here in a bit more detail, Wireshark again tells us what it is, but the client challenge is the 8 bytes of zeros. So that is part of the handshake. And then we get to the authentication. So this is where the actual authenticate function is called. And again, when we get to the client credentials, which is happening down here, we've got 8 bytes. So we're predicting that if we're using an 8-byte client challenge, that we have an 8-byte client credentials. And then we can see the server response. In this case, it is access denied. All right, so there's a real brief overview. Now let's look at a signature that was released for this. So this is the emerging threat signature. Let's break this apart and look at what it's doing. We'll start with this first content match here. So we're looking for content of 00. Now if you With the pipe on either side, this means we're looking for the literal hex value. So we're not looking at anything decoded or ASCII decoded. This is the literal hex value 00 at offset 2. So this is telling us that 2 bytes into the packet, not the whole packet, but the packet payload, we're looking for the value 2. So the payload is starting right here. All this above here, we've got the IP header and the TCP header, and then this is where our payload starts. Again, Wireshark makes this easy. If you've got it up in Wireshark, it'll tell you what each value is. So the payload starts here with an 05, that is our major version number, 00, which is our minor version number, and then we have the packet type. In this case, 00 is a request. So this is offset 2, so that just means that we're looking 2 bytes in. Again, we're looking at offset, so with offsets you always start counting with 0. So 0, 1, and 2. So that's the 00. So that first part of that signature, we're looking for that content 0 offset 2. We're specifically looking for an RPC request. Next we get to this content 1A00, a distance 19 within 2. So the distance 19 tells us that after this we're going to count 19 bytes, and then within 2 bytes of that we're going to have the value we're looking for, this 1A00. So if we count 19 bytes from here, it's going to land us here, and then within 2 bytes we have 1A00. Now it might be important to mention while we're looking at this data that the data in these RPC packets is in Little Endian format, so it's the least significant bit first. So if essentially we're reading it from right to left. So this field, this 1A00 is the entire field. That's the data, but the data doesn't represent 1A00 converted to decimal. It's rather it's 001A converted to decimal, which happens to be 26. And we can see here that is the op number. So we've got op number 26. Now let's switch back to my web browser here, and let's take a look at the Microsoft documentation for this NetLogon RPC. So we've got a list of the op numbers, and we can see that op number 26 is this NetR server authenticate 3. So again, this signature is specifically then looking for RPC request for this net server authenticate function. This is the function that has the vulnerability with the predictable client credential. Okay, so that's where this 1A comes into place. Then we've got another content for 5C00, 5C00. 5C is the hex equivalent to a backslash. So if we look in our packet again, we can see that here. We see this backslash, backslash. And if you've looked at any kind of SMB traffic or RPC traffic, you know that they use null bytes as spacers between each character. So essentially this is just the backslash. Now what is this for? Well, the other data, if we look, we can see it kind of here in the ASCII, but if we actually look at the breakout from Wireshark, we see that we've got a server handle, which is // F Society. Then we have an account name, which is F Society $, and then a computer name F Society. So essentially this is the network location we're logging into. In our test environment, F Society is the name of our domain controller. The account name, so we're logging in as the account F Society $. That $sign tells us this is a computer account versus a user account. And then the computer that we're logging in from. Or at least that we're claiming to log in from. Now the reason for this // doesn't really do a lot for us here, but then for the next section, we've got this content, and we've got these other bytes we're looking for, these 24, some null bytes, and then an 0600, distance 0. So the point of that is essentially this distance 0 just tells us that this content comes at least 0 bytes after this content. So it's just kind of a way to show us that only match if we see this kind of happening sometime after this. All right, so what are we looking for here? Well, this 2400000600, the 24 is this $sign. So this is telling us we're specifically looking for a computer account versus a user account. Then we have the null byte spacing here, and then we get to this 0600. So this is telling the domain controller that what we're logging is in as, essentially what level of access we're looking for, which the 0600 says we're trying to log in as a backup domain controller. So that's again where the vulnerability is. If we can log in as a backup domain controller, we can extract those passwords and do domain admin level things. The last thing we're looking for are the 8 bytes that are part of the client credential. So we can find that here at the end. And then there's just another check, is data at not 5 relative? So that's just saying that after those 8 null bytes, we can count 5 bytes. So we've got 5 more bytes here, this BF, BF, FF, FF, 2F, 21, and then there's no data after that. So we're only trying to match when we're at the end of the packet. Now there's some flaws with that logic. It's not 100%. I've seen some false positives. I'll discuss that in a little bit, but hopefully that explains what it is that this is looking for. Now let's take a look at what we see here to see if what's successful and what's not successful. All right, so here is just the packet capture. It's pretty straightforward. We've got the request, and then we have a response. So if we look at the packet, so we start with the payload, 05 being the major version number, 00 being the minor version number, but this time instead of the 00 indicating a request, this time we have a response. And then we can see at the end of the packet our response code. Again, this is in the packet, it's in Little Indian. Wireshark breaks it out for us in Big Indian, which was what we're used to seeing it as. But the response code is C0000022, which means access denied. If we take a look at the Python script that we're running, we can see that as well. If we get a status code of C0000022, we know access was denied and the attack didn't work. So if you've got a packet capture, or at least you've got response packets, when your IDS triggers on this alert, that's what you're looking for, is that access denied. If it is successful, though, what does that look like? So let's see if we can find one that's successful. So let's see if we can find one that was successful. Now here's a Wireshark query that will make things a little bit easier for you. So if you remember, the op number we were looking at was 26. So we can actually look for NetLogon.op number equals 26 in Wireshark. That's going to give us the request and the responses. So we can see real quickly here, we've got request, and then access denied. We've got the request. Again, all these have that 0 byte or the 8 0 bytes of the client credential, and then access denied, and so on. So to make that even a little bit easier, if we're looking for an instance where it was successful, we can add on to our query and netlogon.rc, rc being the response code, and a 000000000 response code is successful. So this is what a successful request and response looks like. So it was the same. We've got the, major version number, minor version number. We're looking at a response, but then at the very end of the packet is the response code. 4 bytes of zeros is a status of success. The attacker was successful. Okay, so that's analyzing the basic testing script. Now there's another script that is out there that I found that will actually try to exploit this vulnerability. So the second part where you're exploiting it is where you're going to reset the domain controller computer password. So when changing the computer password, there's a different opcode. So we'll look at that. But then at the end of the packet, we're setting the new password, and we've got 512 bytes for the password plus 4 bytes for the password length. And the way we clear that out is we just set all 516 bytes to 0. So that can make this pretty obvious, really, because that's a lot of empty data. Okay, so now I've got another packet capture pulled up. This is a packet capture from the actual exploit script that ran. So the first one was just the Secura testing script. This is actually from that exploit script I was just showing you. So everything starts off the same. We've got the server, the client passing its challenge, which is all 0 bytes again. The server passes its challenge. Then the NetR server authenticate 3 functions called. So again, we've got major version 5, minor version 0. 00 means this is a request. The 18 tells us this is the NetR server authenticate request. We've got the 8-byte zeroed out client credential. And then this is a success, so we see status success. So this happens in the next packet. The server password gets reset. So we start off the same. We've got the major version, minor version, packet type request again. But this time, instead of the op number being the 26, we've got an op number of 1E00, which ends up being 30. Now, if we go back and look at Microsoft's documentation, you can see that the op number 30 is that NetR server password set. So look for that op number 30. That's going to tell you you're looking at the password being reset. And then at the end of this, now Wireshark kind of breaks down here for the password set. It gets confused because this is a malformed packet. But basically what you want to look for after you know that it's op number 30, we've got the same thing where we've got the destination we're logging into, the account name, which is going to be that computer name, which has that, the $sign at the end again, and then the computer we're coming from, or at least the computer we've authenticated as and are pretending to be coming from. Keep that in mind. Don't trust this field. This is essentially what we're hacking. And then at the end we just have the password value, which if they're running this attack is going to be 516 bytes of zeros. Stands out when you're looking at it. It's super obvious. And of course, if it was successful, once again, we get the 4-byte success at the end. Wireshark is having a hard time with this, but that's what we're looking for. So we've got the 4-byte zeros at the end, which means it was a success. So if you're a security analyst and you've seen this signature and you've been trying to figure out how do you analyze it, hopefully this will help. One more thing to look at. I haven't found a lot in the Windows logs that are super obvious. So there's not a specific log I can tell you to look at to say, hey, this attack occurred. But if you are using a platform like Perch, so that's my employer, Perch Security, or some kind of SIEM where you've got Windows logs and IDS data next to each other and you can look at it all in one place, then when this alert triggers, what you want to look for is this event ID 4742. So if you've looked at it and you've determined, okay, they're not just doing the scanning script, someone's actually trying to exploit it. If they exploit it, they're going to be changing that computer account password. When that happens, event ID 4742 should be logged. This is computer account management, and then we can see the account name being changed is this computer account name, so F Society $, and we've got a timestamp for when the password was last set, and this timestamp coincides with when the alert occurred. So I think that about does it. That's everything I've got. If you've got any questions, hit me up on Twitter. If you haven't watched it yet, I recently did a walkthrough of the Houston B-Sides 2020 CTF. That's on my Twitch channel. It's also on YouTube. My Twitter account is @BAMCTF. On Twitch, I'm CTF and Cigars. I'm also BAMCTF on YouTube. If you have any additional content, anything you want me to do a walkthrough or tutorial over, feel free to hit me up on Twitter, and I'll be happy to take a look. And hopefully this will help some of those analysts out there as they work to keep an eye on your own networks and your customers' networks for this specific vulnerability. Remember, always try harder, don't panic, and always, always RTFM.